Afternoon, everyone. It's a pleasure to be here, and I'm really excited to present this work on building a highly scalable and performant priority queue architecture for hardware packet scheduling. This is joint work with my wonderful collaborators, Hugo, Sadok, and my advisor, Professor Justine, both at Carnegie Mellon. So our story today starts with packet scheduling. Over the past 30 years, we witnessed a proliferation of packet scheduling algorithms optimizing for different performance objectives in a variety of network settings. For instance, we have algorithms that impose fairness, optimize flow completion time, perform traffic shaping, or even imbue applications with resilience to adversarial attacks. And this is barely scratching the surface. Now, the key to deployability for any of these algorithms is a programmable hardware packet scheduler. This idea was really brought to fruition by a paper that appeared at SIGCOMM in 2016, which proposed the push-in first-out, or PIFO abstraction for packet scheduling. Here's what it looks like. Let's say you have a packet corresponding to flow C that appears on the wire. In our scheduler, we're going to maintain per flow FIFO queues. And the first thing we're going to do is enqueue this packet into the corresponding flow queue. Now, because this causes C's flow queue to become non-empty, we're going to trigger a small program to compute the rank or priority of this particular flow. Next, we're going to enqueue this flow into a priority queue, which translates the flow priorities or ranks into an actionable packet schedule. In the original PIFO architecture, the priority queue was implemented as an array of elements sorted in increasing order of priority. And this will become relevant shortly. Finally, on the egress side, we're going to dequeue the highest priority flow, which is also the next flow to schedule. So PIFO promises this panacea for packet scheduling. It gives us a powerful abstraction that captures practically any scheduling algorithm that you might care about, and it gives us a way to implement this in hardware at line rate. So, are we done? Well, apparently not. It's been 8 years since the PIFO paper was published, but we're yet to see a switch ASIC that actually implements this abstraction. So this begs the question, why? The culprit is a data structure that lies at the very heart of PIFO, the priority queue. Unfortunately, PIFO's grand vision is hampered by performance, scalability, and resource overhead issues associated with existing hardware priority queue designs. In this talk, I'm going to tell you why existing designs are insufficient when it comes to scheduling in switches and SmartNICs, and then we're going to try to answer this big question of how we can actually get there. So let me start by outlining the requirements, the minimum requirements that modern switches and SmartNICs impose on the scheduler, and transitively the underlying priority queue. The first key requirement is scalability. Any practical scheduler needs to support the flow counts that we see in today's networks. For instance, NVIDIA's Spectrum SN4700 switch, which is a state-of-the-art 32 by 400 Gbps switch, has a unified packet buffer that's capable of storing over 100,000 packets. Each of those packets might correspond to a distinct flow, and so our scheduler needs to support priority queuing for over 100,000 flows. The next key requirement is performance. In order to keep up with the switch backplane or the NIC data plane, our scheduler needs to support, or our priority queue instance needs to support scheduling at today's modern line rates, which is at least 100 Gbps for both switches and SmartNICs. And the final key requirement is this feature that we call logical partitioning. Logical partitioning refers to the ability to statistically multiplex a single physical priority queue between many logically independent priority queues. It turns out that logical partitioning is a hard requirement for switches, and any priority queue that doesn't support this feature would require far too many replicas to even fit on the chip. Okay, so why don't existing designs work? To answer this, let's revisit PIFO's priority queue architecture. I told you earlier that PIFO implements its priority queue as an array of elements sorted in increasing order of priority. I'm showing you the structure here. So we have the letter corresponds to the flow ID, the number corresponds to the priority, and you can see that these are flows arranged in increasing order of priority. When a new element, in this case L with priority 4, arrives, PIFO uses an array of comparators in parallel to decide where to insert this incoming entry. The problem is that each of these comparators is an expensive circuit, is an expensive hardware circuit that is complex and expensive to synthesize. So this is the more comparators you have, the worse performance gets. This might remind you of the n log n complexity lower bound imposed by comparison-based sorting. And what we're seeing here is precisely the hardware version of this. With PIFO, we hit a hard limit with 4K flows, beyond which the circuit simply won't synthesize. Since 2016, several priority queue designs have sought to improve upon PIFO's priority queue architecture using more sophisticated parallelization techniques. For instance, PIEO, which appeared at SIGCOMM in 2019, re-architected the PIFO's ordered list into a 2D matrix, thereby reducing the number of parallel comparators on the critical path. BMW-Tree, a paper that appeared at SIGCOMM last year, reduced this even further by re-architecting the list into a k-array tree of unordered arrays. So this line of work represents a concerted effort to improve upon the scalability aspect of PIFO's design. And indeed, we see progressively better scaling, all the way up to 100,000 flows. The problem is that these designs give up some feature or another in exchange for scalability. For instance, PIEO achieves a maximum packet rate of 15 million packets per second on an FPGA SmartNIC. This corresponds to roughly 10% of the line rate, even at 100 Gbps, which is commodity nowadays. On the other hand, BMW-Tree gives up logical partitioning. This means that it would require over 1,000 replicas of the priority queue in order to both support incast as well as implement output queuing on a 32-port switch. This corresponds to roughly 1.5 to 6x the chip area to do priority queuing alone, making it impractical for switch deployment. So the big question is, how do we satisfy these very tight constraints? The key idea is that if the priority span is bounded, as it tends to be for many networked applications, we can achieve all three properties using non-comparison-based sorting. So let's see how this alternative to comparison-based sorting, a technique known as integer priority queuing, works in practice. Let's say we only wanted to support 4 priorities in the range between 0 and 3. We're going to maintain an array of priority buckets, as I'm showing here, where every bucket is implemented using a linked list. When a flow B with priority 0 arrives, we're going to index into this array and simply enqueue this flow into the list. Similarly, if flows A and C with priority 2 arrive, we're going to index into the list, index into the array, and enqueue them at the corresponding priority bucket. So enqueuing is simple. Now, in order to implement a priority queue, we also want to be able to dequeue the highest priority element. A straightforward way to implement this is to iterate over the buckets in decreasing order of priority, stopping at the first non-empty bucket. The problem is that this is going to be slow, because in the worst case, we might have to traverse all the buckets. A better strategy is to augment this structure with a 4-bit bitmap, as I'm showing here. So each bit in this bitmap encodes the occupancy of the corresponding priority bucket. For instance, we're going to set the bits corresponding to priorities 0 and 2 to 1, indicating that the buckets are not empty, whereas the other bits are set to 0, encoding the fact that the priority buckets are empty. Now, in order to locate the highest priority non-empty bucket, we can leverage this operation called a find first set, or FFS for short. This returns the index of the leftmost set bit, corresponding to this priority bucket, from which we can use to simply pop the list. We can implement find first set in logarithmic time using a binary search-like algorithm, making it a lot more efficient than the iterative search I showed you earlier. So this is great for small priority spans. But what if I wanted to support a huge number of priorities? Let's say 32,000. Unfortunately, due to limitations on the word size that hardware can efficiently operate on, we can't simply perform find first set on a 32K bitmap. Our hardware would really not be happy. Instead, we can turn to recursion. So suppose now that we wanted to support 8 priorities in the range from 0 to 7. As before, we're going to maintain our array of priority buckets, augmented with the bitmaps encoding occupancy. But now we're going to construct a tree of bitmaps, where every bit in a non-leaf bitmap encodes the occupancy of the entire subtree rooted at that node. So for instance, in this example, we've set the bit in the top level bitmap to 1, indicating that the entire subtree has at least 1 entry. In this case, it has 3. Conversely, we've set the left bit to 0, indicating that the entire subtree is empty. Now, in order to locate the highest priority non-empty bucket, we can recursively perform find first set starting from the root, which leads us to the priority bucket corresponding to priority 2, from which we can simply dequeue the highest priority element. The data structure I just described to you is called a hierarchical find first set queue, or HFFS for short. It uses a counting sort-like algorithm to implement priority queuing, thereby subverting the complexity barrier imposed by comparison-based sorting. This brings us to our design, which we call the bitmap bucket queue, or BBQ for short, which is inspired by HFFS queues. Now, we're not the first to notice that using a priority queue with constant worst-case time complexity is a good idea for scheduling. Many software systems have in the past used FFS-based queuing to great success. For example, the Linux scheduler uses an FFS queue for process scheduling, and IFL, which was a paper that appeared at NSDI in 2019, has also applied it for software packet scheduling. Our key insight is that this data structure is amenable to a high-performance, fully pipelined hardware implementation, allowing it to satisfy the tight constraints that we had sought out to meet earlier. So how does BBQ satisfy these constraints? The first property that we wanted, scalability, actually comes for free. BBQ's IPQ-based design breaks the dependence between the queue size and the runtime complexity of operations, allowing us to support a large number of flows without incurring a performance cost. So scalability simply falls out of this high-level design choice, allowing us to optimize for the other two objectives. The second property we wanted was performance. Unfortunately, performance is not so cut and dry, especially in hardware. It's actually a combination of two independent metrics. The first one is the operating frequency, or Fmax, of the circuit. This is measured in megahertz and is analogous to your processor's clock frequency. The second is the operations per cycle, or OPC. This is the number of operations that complete every cycle after accounting for inefficiencies such as pipeline stalls, bubbles, flushes, and so on and so forth. And finally, performance measured in operations per second is the product of these two independent metrics. And we really need to optimize for both of them. BBQ achieves a high operating frequency by using a deep pipeline, where each stage of the pipeline is designed to be as small and do as little work as possible. And the pipeline stage is also designed to be roughly equal size. So this translates to taking this high-level data structure on the left and carefully constructing a deep hardware pipeline that is optimized for performance. It's deep in the sense that there are many stages. So for instance, we use a 11-stage hardware pipeline for a 2-level BBQ. However, this is not enough by itself. It doesn't matter if your Fmax is high if you can only do one operation every 11 cycles. What we really need is for multiple stages of the pipeline to be active concurrently, a technique known as pipeline parallelism. BBQ realizes a fully pipelined architecture, which means that it can do one operation every cycle independent of workload and without any pipeline stalls, flushes, or bubbles. So pipeline parallelism is actually key to BBQ's performance. Unfortunately, pipelining is hard, and the issues that arise from pipelining are precisely what makes BBQ's design both interesting and challenging. So looking at this data structure here, it might seem like everything is nice and modular, but in reality, we encounter a horde of issues when we try to extract pipeline parallelism out of this. Unfortunately, I don't have time to talk about this today, but we use a variety of architectural techniques, such as speculation, water level marking, operation coloring, and so on and so forth, to fully pipeline this design. If you're interested, please come talk to me at the poster session or read the paper for details. The final feature that we wanted to achieve was logical partitioning. BBQ's design makes it amenable to supporting logical partitioning with zero fragmentation of queue memory or resource overhead. The idea is to partition the physical the priority span of the physical BBQ into independent logical partitions. This allows us to map logical BBQs to disjoint ranges in the priority span, and they all share the same set of resources of the underlying BBQ, but operate completely independently of one another. And then we can use simple steering logic composed of bit masking operations in order to route operations to the correct logical BBQs. So in summary, BBQ's integer priority queue-based design allows it to scale to a very large number of flows, in this case, our target being over 100,000. It achieves a single instance performance of 150 million packets per second, or 100 Gbps line rate on FPGA SmartNICs, and 1.5 billion packets per second, or 1 terabit per second on switch ASICs. And finally, BBQ's unique priority index structure allows logical partitioning with no fragmentation of queue memory or performance overhead. So the easiest way to make sense of these numbers is to put them in the context of existing state-of-the-art designs. So I'm going to present a brief evaluation in the context of FPGAs. We implemented BBQ in System Verilog and synthesized it targeting a state-of-the-art Stratix 10 MX FPGA. And we did the same for our baseline designs. So in this graph, I'm going to show you the throughput in millions of packets per second as a function of the queue size. I'm also highlighting the 100 GBE, or the 100 gigabit per second Ethernet line, and the precision corresponds to the number of priorities we can support. So in this case, we have 15 bits of precision, which means we can support 2 to the 15, or 32,000 priorities. So as far as baseline designs go, we see that PIFO is actually state-of-the-art in terms of performance. It achieves, at small queue sizes, it can achieve a throughput of 200 million packets per second, and very quickly deteriorates as the queue size grows. Conversely, BMW-Tree is actually state-of-the-art in terms of scalability, achieving over 100,000 entries. BBQ achieves the best of both worlds. At small queue sizes, it meets or exceeds PIFO's performance while scaling similarly to BMW-Tree. One point I want to highlight here is the 100K entry point, so or 2 to the 17 entries, where BBQ can sustain 100 Gbps with over 32,000 priorities, corresponding to 3x the packet rate of state-of-the-art designs. So in summary, I told you that existing priority queue designs don't meet the stringent requirements imposed by modern switches and SmartNICs. In this work, we designed BBQ, an integer priority queue, which for the first time makes it feasible to implement priority queuing on these line rate switches and SmartNICs. BBQ supports over 100,000 entries with 32,000 priorities at 100 Gbps line rate, or 150 million packets per second on an FPGA, and 1 terabit per second, or 1.5 billion packets per second on a switch ASIC. These are my wonderful collaborators. Here is a link to our open source code, and I'm happy to take any questions.